Welcome to solverfy.
Okay, in this problem we have a hydrogen atom with a mass of just a proton, 1.67 times 10 to the negative 27 kilograms. And this hydrogen atom emits a photon with an energy of 10.2 eV. We are asked to find numerous things. Namely, we want to find the kinetic energy of this hydrogen atom, which will recoil after firing off this electron. And the reason why it will recoil is through conservation of momentum. If it releases an electron with some momentum, it has to have an opposite momentum to maintain conservation of momentum. So it'll have a resulting kinetic energy. And we want to get the ratio of its kinetic energy to its total energy to determine if this recoil effect is going to be important enough to consider for a photon emitted at this energy. So for equations, we need to know the energy and momentum of a photon given in terms of the Planck constant and its wavelength. We'll need to know the kinetic energy and momentum for a particle with mass, which is the simple non-relativistic expression. And I strongly believe that non-relativistic equations will be appropriate for this particular situation, because I do not think that this mass is going to have much velocity. So let's jump into it. To start off, ultimately we want to use momentum, but in order to get the momentum of a photon, we need to know its wavelength. So we can start by taking its energy, E equals hc over lambda, and we can use this to find lambda, which is hc over E. And so numerically, we'd actually need to use Planck's constant in its EV form, 4.135 times 10 to the negative 15 electron volts seconds, multiplied by the speed of light, 3 times 10 to the 8 meters per second, all divided by the stated 10.2 eV. And this would give us a wavelength of about 1.22 times 10 to the negative 7 meters. So now we can set up conservation of momentum. So the momentum of the photon, which is h over lambda, is going to be equal to the momentum of the particle with mass, the hydrogen atom, mv. We know everything except for v, which is what we solve for. V is h over m lambda. And it will come out to be about 3.25 meters per second. So quite slow, as I predicted. This is why relativistic effects won't play a major role. So now that we know V, we can find the kinetic energy of our hydrogen atom, 1/2 mv squared. Plugging in m and v, we will get a result of k equals about 8.8 times 10 to the negative 27 joules. And we can convert this into electrons by dividing by 1.6 times 10 to the negative 19 joules per electron volt. We get 5.53 times 10 to the negative 8 electron volts. So this is an incredibly small number, which tells us that this kinetic energy of the recoil is going to be negligible. It's very, very small. So we can get the ratio of kinetic energy to energy of the photon, which will be about 5.42 times 10 to the negative 9 So clearly, while there's equal momentum being imparted to the hydrogen atom, because its mass is so large, that translates to a very, very tiny velocity that's imparted, thus a very, very small kinetic energy. So this recoil effect in terms of energy will be negligible. It's barely going to move this atom. And that's the main result. We got wavelength, that's important. Velocity, that's important. Kinetic energy, that's most important. And that's it. Thank you very much.